Okay, recall what we learned last time. Let's do a quick recall. Last time we learned, kind of summarize why we learned engineering materials. Then we kind of put materials in different categories, right? Metal, ceramics, and polymers, and some advanced materials such as semiconductor, biomaterials, and smart materials. Then after that, we watched the video, right? On video, hopefully that's pretty boring, right? Watch people doing mechanical testing, which is called, what's the name of the test? Anybody knows? One of the most important tests, pencil test, right? Pencil test. And they have a metal bar, and that machine's grabbed on both ends of that metal bar, pulling it at tension force on each end, and you will see the deformation of that bar, and it breaks at one point. It generates a plot or diagram. And I told you, remember the shape of that diagram, because we're going to talk about the details about that diagram. And then you have a lot of questions about pencil test, but hopefully today's class will answer some of those questions. The guys in the back row, are you guys, can you guys hear me? Okay, all right. Okay, let's draw the diagram here. The most important diagram for mechanical engineers. Stress, strain, or you can just call it curve or diagram, whatever you want to call it. So on the y-axis, we have stress. We use the symbol sigma. On the x-axis, we have strain. And we use the symbols epsilon. Am I call this right? It's called epsilon. Okay, and anybody remember how that curve looked like from Wednesday? Curve. Where should the curve start? It should start from the origin, right? And go up, kind of linear increasing at the beginning. Then it drops. It breaks at one point. Okay. The only difference between what I'm drawing here and the video you watched on Wednesdays. On Wednesday's video, here is what? It's now called strain. You remember what's that? Elongation, the change of length, or elongation. Delta L, remember that? What is the unit of name there from the video? Force instead of stress. So that's what we are going to talk about. What is going on here? Why we have stress and strain instead of force and change of length. Have you took statics before this class? How many of you already have statics? Or already taking it? Okay, all right. And I think at the end of the statics, you will learn stress. But at this point, you're dealing with forces. So stress, you can think about stress, it's an intensity of force. I would think about it that way. So it's kind of like intensity of force. The mathematical expression is going to be sigma equals force divided by area. So that's a mathematical expression, force divided by area. And that area A is the area your force is applied on. So for that video, we have a metal bar, and A should be the cross-sectional area of that metal bar. And say, if I use my push on this table, what's the stress going to be? What area will actually use? If I use my hand push on this table, the area should be the area of my hand, right? Instead of the table. Okay, remember that that should be the area that force is applied on. And that tells you the intensity of the force. Why do we want to know the intensity of the force? Don't you think force is enough to express the load? Who likes to cook? I love cooking. And you know the worst part? I don't like washing dishes. I don't like cutting vegetables. And the way you cut, the one reason I don't like cut vegetables and meat, I don't own a very good knife. Good knives can be very expensive, very sharp. Why do you want to have a sharp knife to cut vegetables? It's easy. Well, if you have a very dull knife, you can still cut things, but you need more force, right? So that's what we're doing here. We're trying to decrease this area so that we can apply a smaller force to reach a large stress, if that makes sense. For those who next to the videos, TVs, you can turn on the TV so the kids in the back row can see better. Okay, so that gives you a sense that why we want to use stress instead of force. All right, thank you. All right, another thing we want to talk about is strain. Strain. I would think strain kind of similar to stress. Strain. So strain is similar to stress. It's you can use strain to express the intensity of change of momentum. Yeah. The strain is intensity of how much the change of length. Why we want to have strain instead of just using change of length? Yes. So the change of length is relative. So for example, yeah, if I have this pen, we're talking about 2 millimeters of change of length. You can't tell by naked eyes, right? It's really tiny. But what if I have a piece of material that is only 5 millimeters long, and I tell you there's a 2 millimeters of change of length? That could be very significant just for that 5 millimeters, right? That's awesome. 1%. I don't know. But that gives you a sense. If you only use change of length, that's not enough to describe if that is large. Change of length is large or small. That's why we want to kind of have a to show the intensity. Is this change of length large or small? That's why you use strain. It's defined by delta L, or delta, change of length, divided by original length. Here we can write out the change delta L. Delta L would be the length after deformation minus its original length. So L O is the original length. So delta L equals L1, which is the length after you apply a force, minus L0. Okay, so those are the definitions of stress and strain. Now I want to ask you, what are the units for stress and strain? Let's start with stress first. What is the unit for stress? Yeah, newtons per meter squared. Force has the unit of Newton. Area, and use meter square. There you go, you have the units for stress. But this is not very commonly used for stress strain curves. In stress strain curves, you would say stress in terms of pascals or kilopascals, or sometimes gigapascals. Or sometimes you will see PSI. But they're all the units for stress. Okay. And sometimes you will see megapascal as well. All right, units for stress is not too bad. What is the unit for strain? Unitless? Is it unitless? And to look at that, find out what's the unit for strain. So on the top, delta L, what's the unit of L1 minus L0? Meters. What's the unit of L0? Meters. Meters. Cancel off nothing. Yes, it's unitless. All you can see the unit is 1. Doesn't have a unit. All right. Okay, good. Now we understand on X direction we have stress. On X direction we have strain. On Y direction we have stress. Now let's look at more details of this stress strain curve. Make sure I'm recording. Okay, good. Okay. Okay, what I'm drawing here is an ideal kind of stress strain curve. Just want to show you different characters on this curve. First, can you identify where is the region that has plastic deformation? Where is another region that only has elastic deformation? But first, what is elastic deformation? It's kind of like a spring. When you stretch it or compress it, it changes length. But when you release the force, it can go back to its original length, right? That's if it can recover 100%, that is elastic deformation. If something couldn't go back its shape after you apply the force, that is permanent deformation or plastic deformation. So in this curve, start from here. Before this dashed line, you would have, this is called elastic region, and that shows the elastic behavior of the material. After this dashed line, all the way to the end of the curve, this is a plastic deformation area. Okay, so another way to test this, if I apply a stress, which is that large, somewhere is around there. Then the stress, the corresponding of the curve will be inside of the plastic region. Then all the deformation caused by that stress, it's prominent deformation. But if you can apply a stress and within that's below that point, anywhere here, and the corresponding strain will be inside of elastic region. It can recover to original shape. And this area with a flat curve, this is called yielding. We're going to talk about what is that later. From this orange line all the way to this maximum stress, let's use a different color. And this region is also called strain hardening. And the last region here between the blue line and the red line, dashed line, it's called necking. Since we both watched the video on Wednesday, we know what is necking, right? The radius reduces with increasing the force. All right, those are kind of the different regions on the stress strain curve. Elastic region, plastic region. If you look into the plastic region, yielding, strain hardening, and neck. And there are a couple of important points on this curve. The first point, it's somewhere inside of this elastic linear line. Somewhere here, the end of the linear line, the straight line, that gives you the proportional limit, the corresponding stress. Let's call this PL. And so P rho PL proportional. Another point is right after it. The corresponding stress, let's call this, oh, actually there's no special name, let's just call it E. This stress is called elastic limit stress. Another point, which is right at the beginning of the yielding region,
and we have yielding strength. This is one of the most important point on the curve. It's called E sigma Y. And sometimes, more realistically, pretty hard to tell these three different stress apart. For some materials, they probably only have the proportional limit point, or you only have the yielding point, or another point. Barely to see three of them there on the screen. But I just want to let you know, an ideal stress strain curve should have those 3 points. Tell you those informations. Another important point is this maximum stress right there. It's called tensile strength or ultimate strength. Sometimes you will see sigma U, or sometimes you will see TS. This is for ultimate stress. We have one more. So what happens at the end of this curve? Failure breaks, right? That metal bar broken into 2 pieces. So right here, we have a fractal stress. Sigma F. You can also find sigma F on the Y direction. Should be somewhere over there. Sigma F. Okay. Those are all the very important information you can read from the diagram. And make sure familiar yourself with this diagram, with all the names, all the terms. So in our exam or quizzes, I can give you a blank curve, and then you tell me which point, what's the name of each point or each region. Does that make sense? Okay. All right. Another thing I want you to understand is this curve, each curve represents the property of a single type of material. If you change a different material, you're going to have a different curve. Even a same material, let's say steel, you could end up with different curves, different steel curve, by having different content of carbon or other added impurities inside of steel. So that could change the shape of the curve. Everybody have this writing down your notes? Okay. Okay, there are a couple of different types of curves you will see in this class or somewhere else. Remember last time in that video, there's a curve, has maximum point and it drops and fractures and goes like that. And sometimes you won't see that in other type of materials. You only see a very smooth transition between the linear and non-linear region. And for the first type of stress strain curve, it's a little bit hard to define where's the yielding stress. If you come back here, yielding stress, it's kind of the transition point between the linear and nonlinear region. So in order to do that, you need to find where's the maximum stress, which is that point, and also find out where's the minimum stress in between this zone, where it should be somewhere around there. Then you take an average between those. You add them together, divided by 2, you get an average stress, and that would be your yielding stress. Then what happens if you have a curve that doesn't have that kind of region, look like that, drops? It's a smooth transition. If you have a smooth transition like this, and you would need to use a technique, it's called 0.2% offset. You mentioned in the video, right? I told you probably doesn't make sense, but now it makes sense. So in that case, you need to find where is the 0.2% strain on the x direction. So for example, this point right there is 0.0002. If you times that by 100%, that will give you 0.2%. So identify that point, that strain. Then you draw a parallel line. This line, the dashed line, must be parallel to this straight line here. And this dashed line will have the intersection with the curve, which is right there. And you need to rate out what is the corresponding strain. And that's how you find the yielding strain. That's why it's called 0.2% offset yielding strain. All right, we could have other types of stress strain curves. We can have a curve like this, very short. What happens? It's probably a very brittle material, and when you apply force, stress, it just breaks right away without large deformation. And we could also have a very ductile material that give you a stress strain curve like that. You can apply the stress to this material. This material will experience a large deformation before it breaks. It's right there. But it could have a much smaller ultimate strength, fracture stress, or yielding stress than this very brittle material. You could also have materials in between. All that. It's all possible, depends on the property of the material. But if you're doing experiment and you're testing a new material and you find out your stress strain curve look like that, then either there's something wrong with the test, or you're gonna get your next Nobel Prize. Imagine if you have a stress strain curve like that. What is happening there?
It's somehow coming back.
Oh, yeah.
Over and over.
So it looks like it's gonna break and then become strong again. And then you keep adding load and then weak and strong again. So it doesn't make sense. I don't know. I never seen material like that, but we won't see something like that. Okay. Any questions for stress strain curve before we keep talking? Okay. Now let's explain some of the words yielding property limits or yielding strengths. So yielding is when the stress level at which plastic deformation begins. You can refer that back to the diagram. Just draw yielding. That's where the plastic deformation starts. That's a yielding. Okay. And for yielding strengths, we just explained, and it's a starting point. It's right at that point where this region starts, and that yielding points can be difficult to determine. We mentioned if you have this case, you're gonna have if you have those two different cases, you can have different methods to determine the yielding strengths. And it's pretty hard to determine at reality. And if sometimes a lot of materials, they don't really have a point that you can just read off from the diagram. So for nonlinear elastic materials, you're going to use a method it's called 0.005 offset, or you can call 0.5% offset strain. Or you can use the method we just mentioned. You find the upper yielding stress and you find the lower yielding strengths and find the average. Of course, for the linear elastic materials, we use the 0.002 or 0.2% offset method to find strain. All right. Now let's do some real practice to see how to read the stress strain curve. Okay. Oh. Find that. Right. No. Yes. Okay. So this is the stress strain curve of steel. One type of the steel I found is on Google. And let's do some practice with this. Here we have a spring. You know this. This we have megapascal, which is our stress. That's how do we find yielding stress for this material? Yeah. In order to find yielding stress, first look at this curve. This curve has a smooth transition between the linear and nonlinear region. So we want to use the 0.2% offset, 0.2% offset spring. So what to do? How to do that? What's the first step? First step, come to this x-axis, find out where's the 0.2% strain. 0.2% is 0.002. So which is this point, right? Right there. And what should we do next? Yes, now we draw a line that's parallel to this. The parallel line, we will have intersection with that curve somewhere. Oh, you find the intersection, and you read off from the diagram of what is corresponding stress. It's approximately around 300 megapascal. So I can say, well, I think this is tilted, but it's probably somewhere around here, 310 maybe. We can see our yielding strength for this material, the steel here, it's about 310 megapascal. Okay. I have a question. Why we want to have a stress strain curve? We talk a lot about the details of stress strain curve. What we can use them about. So as long as someone did this test for this material, this type of steel, then you don't have to do the test again. You can just grab that diagram from your mechanical engineering design. For example, you want to use the same material to design a beam of the back of the table or something like that. And you know the load you apply to that beam. The beam is under tension stress, tension force. And you can refer this diagram, find out what is the depth deformation you can get under that stress without holding the experiment. Does that make sense? So for example, if we're designing a bridge, we need a beam, steel beam with exactly the same material. And if we want to apply a 250 megapascal stress, can you find out what is the strain under that stress? So first, find where's 250 megapascal on the y direction. 150. 30 for each intervals. That's 180, 110, 140, somewhere around there, right? And you find where's 150. Then come to this curve, find its corresponding strain. One in the vertical line. Okay, you find it, it's somewhere around here. It's 1,001 something. Let's see. 1,0015, and that's the strain under that stress. if your beam is 1 meter long, now I want you to do some calculation on your notebook to find out what exactly is the new length of your beam under this stress. If your beam is 1 meter long.
You got 1 minute to do the quick calculation, find out what is the new length of your beam. 1 meter long beam under this 250 megapascal stress. Got it? Okay. What's the answer? 1.0015 meters. Why is that? Anybody knows how to do that?
So, we found the strain. We have the equation for the strain, that the strain equals, the final length minus the original length.
Pretty straightforward calculation. Let me just write it out very quick. So we know the strain, which is sigma. We read that from the diagram, which is 0.0015. And this strain from the definition equals the change of length delta L divided by the original length. The original length is 1 meter. It's 1 meter. On the top, delta L can be written as the new length minus the original length, L1 minus L0, which is 1 meter. And here, L1 is something we're trying to find. What's the new length under that stress? Oops. This whole thing equals 0.0015. And solve for L1 just by using 1 meter plus 0.0015 meter. Get 1.0015 meter long. That's your deformation under this strain, under this stress. Is that deformation plastic or elastic? Is that a plastic deformation or elastic deformation? Elastic, raise your hand. Plastic, raise your hand. Okay. Come back to the diagram. 250. That is somewhere
around there, right?
That was my.
That's kind of passing the elastic region. Elastic, you need to look at where's the linear region of this curve. I think the linear region, well, you can't totally read this. I think the point I take is a little bit tricky. I think the linear regions stop somewhere around there. So if you apply a stress larger than that level, then you're going to have plastic deformation. If you apply a stress lower than that point, you can have elastic deformation.
All right. So next time we're going to keep talking about stress strain curve. That's all for today. But before you go, I want to do a quick name call and tell you the homeworks. And I think we have a homework due today by 4 p.m., right? And also, I want to do another homework is, how many of you already have a textbook? Raise your hand. Okay, your weekend homework is going to be read chapter 6, mechanical properties. Read your textbook, and I will post the homework on Moodle. So you're going to have homeworks. I'm going to write all the numbers out. I'm going to check your post on Moodle. Try to do them. We haven't touched some of the topics, but as long as from today, you should able to solve 1 or 2. Okay, that's about the homework. Let's do a quick name finding. Lynn, L-Y-N. Is Lynn here? No. Shelton Bell. Matthew Burns. Isabella. Ella. Dylan. Earth. Mandy. Andrew Fisher. Victoria. Chloe. Haley. And Lane. Got the name right. Garrett. Reed. W-A-D-E. No, oh, sorry. Robert. Potter. Peter. Nash. Gilden. Catherine. Lucas. Jacob Shooter. And Nathan. Alex Taylor. Okay. Was there? Okay. Miles. Ellie. Samantha. Michael Watson. Justin Val. Alina. And Michael Rose. Awesome. Okay, thank you guys. Have a good weekend.